So welcome everyone. I'm Philippa Jefferies and I'm here with Anand Prasad, also from Cybersecurity magazine, and we are talking to Nigel Smart, professor at KU Leuven, about data privacy and privacy enhancing technologies. So welcome Nigel, thank you so much for joining us today.
Cool, it's great to be here. Thank you. Thank you for inviting me.
Yeah, so to start with, kind of in your view, what does privacy really mean when it comes to data and so on?
Oh, well, that's a really good question.
Okay.
In some sense, it's a very loaded word, and so actually, so you have privacy when you kind of say in normal discourse. What you kind of mean is your personal information. You mean stuff about you, your genes, your age, your sex, your religious affiliations, or all sorts of things like that. But when it comes to, I mean it in tech, actually, in terms of privacy enhancing technologies, actually the word privacy is slightly confusing because we don't necessarily mean private data. What we mean is data that you want to share with someone, that you want to share the result of sharing the data, but not the data. So it's not necessarily private information. It just means that there might be some business reason you might want to share it. So to me, it's actually better when you talk about PETs, privacy enhancing technologies, is the P actually stands for partnership.
Okay.
It's really about bringing people together to form partnerships such that they don't actually have to give away all of their data to actually form the partnership. But what you're really doing is you're enabling partnerships to happen.
Okay, yeah, so when we think of privacy normally, it's about kind of almost hiding your data, stopping other people from seeing it, but actually it's about sharing it, but
not sharing
kind of
it
within
sharing it,
creating
but not
partnerships so people are privy to what they need to be and not to.
It's unlocking the utility of multiple parties' data without actually unlocking the data.
So examples are thinking what kind of banking information, medical information?
Oh, that's a really good example. So a real classic example here is anti-money laundering. So, for example, with anti-money laundering, you want, criminals, they launder money by passing it through the banking network. And they don't pass it through the banking network of one bank, they pass it through the banking network of many banks. So actually what you want to do is you want to pool all the bank's information to find out where the criminal behaviour is happening, but you want to do this in a way that one bank's customers are not revealed, and their bank balances in their accounts and all their transactions are not revealed to the other bank. That's a really good example.
And did you want to say something, sir?
Yeah, I mean, actually, I was also going to request Nigel for some examples and explanation this side, but this banking industry certainly, I think, is probably the most important one as we discussed, and that hits actually all of us in our life here. But do you also see the same kind of examples in healthcare as Philippa was mentioning?
Yeah, exactly. So the classic example, which all academics use, is the idea of you want to pool data in healthcare. So, for example, you might have hospital information about patients, and you might want to create aggregate information for the whole population. What interventions work, what interventions don't work. By pooling data, or you might want drug companies want to kind of pool their toxicology tests on various combinations of chemicals without actually revealing what chemicals they're actually testing for new drugs. So there's lots of applications. You pick a vertical segment, we can come up with an application.
That's really good to hear. I was just thinking about how these privacy things are changing over time. Long back when I was talking to friends, we would also talk about like IP address being private or not. So to someone, because that could lead to lead to some identification. And we used to talk about and I picked up health because of a reason actually. If you talk about health, then one would say there's a trade-off between if you want healthcare and privacy. So,
yeah. So I think, like I go back to the beginning, the idea of PET technologies is to unlock utility without unlocking the data. So you get good healthcare, but you don't reveal your health information. The thing about IP addresses is really interesting because privacy also means keeping your IP address secret in some sense. And so when we talk about privacy enhancing technologies in the commercial world, what we mean is things which allow us to compute on data without revealing information. So technologies like MPC, FHE, zero knowledge, etc. Whereas there's another lot of privacy enhancing technologies which are just sort of like privacy technologies like Tor or whatever, which actually protect your IP address. And so you often, this is why I think privacy is not a very good word, is because they're used in both contexts and people then get confused about the technology and what are you protecting, etc. But you don't really use Tor to create partnerships. You use Tor to protect your IP address, so, or your patterns of behavior. So I think that's why partnerships is a better description here, because it avoids this confusion.
I think I really appreciate that differentiation. That helps everyone who's listening to it, that we shouldn't just use privacy just like that. And
yeah, exactly.
Several meanings. So it's a loaded word, let's put it that way, in many
yeah,
definitely. You kind of listed some just now, but when we talk about privacy or partnership enhancing technologies, what kind of technologies are we talking about? Can you kind of give us some examples?
So they're all kind of really, it's a really weird landscape, because there are all technologies which 10 years ago were considered pie in the sky, that they were considered academically, they'd been invented in the 80s or around that time, but everyone thought they weren't practical. And so what we can now, over the last 10 years, we can now make massive improvements have been made, such they're now being deployed. So for example, I'll go through the three which I just listed, which are the kind of classics. So one is multi-party computation. Now this basically is a technology which allows multiple parties to come together to pool their data and extract value from it. So basically it's bringing people together, and between them they execute a protocol to compute whatever function they want on the data. A classic example here would be electronic voting. You want everybody to come together, pool their votes. You don't want the votes to be public, but you want the result to be public. And so that's an example of a multi-party computation. Now, the next example would be homomorphic encryption. Now, homomorphic encryption does exactly what it says on the tin. It encrypts data. So I encrypt data, and I can now send this data to some other party who cannot see the data, but they can now compute a function on the data, but they don't get the result of the function. What they get is an encryption of the result of the function, which then has to be returned back to me for decryption. So what this allows me to do is to outsource computation to someone. I can send some data. So for example, I could encrypt my health record, send it to the cloud, who could then apply some machine learning algorithm on it, send the result back to me, and then I would now decrypt it, and it would tell me whether I have cancer or not, say.
Okay, but they're never privy to the data.
They're never privy to the data, and they're never even privy to the result either. And then the third technique is what's called zero knowledge proof, which is actually being deployed a lot in blockchain applications. And what a zero knowledge proof allows me to do is I can compute on my private data and give you a result of a function. And then I can prove to you that I actually computed that result correctly. You don't know what the input to the function was. So an example here is that I could prove to you that I have enough money in my bank account to do a certain transaction without actually revealing how much money is in my bank account. So you now have confidence that something that I'm credit worthy. So you can imagine this as a credit score thing. Is I put data into a credit score, and I can prove to you that I have the right credit without actually revealing the private information.
Okay. Interesting. And in your opinion, how well do these things work? Are they very successful? Are they kind of issues that
there are issues in terms of how widely so there's depends what you mean by the question.
Sorry, it's a very open question.
It's a very open question. So on one hand, what is amazing about these technologies is that we can do anything with them in theory. So in theory, you can compute any function you want in in any of the three technologies. The thing is in practice, that's not possible.
Yeah.
There's limited, so they're not a magic bullet that solves everything. So what happens is that for zero knowledge, we can do very, very complex functions, and this is why it's been widely deployed on the blockchain. For MPC, we can do relatively complex functions. And for FHE, at the moment, it's very much for point solutions. So it's kind of like in a very, very specific use case, you can do some really interesting things, but it's very use case specific. And so there's a lot of work at the moment in homomorphic encryption in trying to create hardware accelerators to make it go very fast. There's a big US government program in this space funded by DARPA, which is trying to build accelerators for homomorphic encryption.
So is processing a limit for all three of them, or it's especially for the homomorphic encryption that we are talking about?
There's a limit to all three of them, but the limit is more pronounced in homomorphic encryption. So with all of them, so with zero knowledge, you can compute amazingly complex things. For multi-party computation, you can compute slightly complex things. And homomorphic encryption, you can compute at the moment very specific things. And so the sweet spot really depends at the moment on the specific application, but they're being widely deployed in all sorts of applications. We're seeing a number of companies in the homomorphic encryption space selling solutions and developing technology. There's a huge number of companies in the MPC space selling various MPC solutions in different vertical markets. There's lots of applications, as I said, in zero knowledge in the blockchain space. There are huge investments by government and legislation going through that kind of will facilitate the use of these technologies in other applications. So this really is, very, very wide range of applications we can use them in.
Okay, so actually the limit I was thinking is might be there, but these are already quite practical.
Yeah. And a real classic example where I said, homomorphic encryption is quite limited, but you actually probably use it every day because inside the Edge browser there is there's a methodology to check whether when you enter a new password whether it comes on a blacklist, and that's implemented using homomorphic encryption. So if you use Microsoft Edge, you are already using homomorphic encryption in some example on a daily basis. So it really, homomorphic encryption is the least applicable at the moment, and yet you are already using it. So these technologies are already out there.
So if I may ask in these lines further, one thing is the limitations part, and that's very clear that it has become very practical now and being used even in the browsers. On the other side, do you see any kind of security attacks possible on these kind of solutions on MPC?
In some sense, what it does is it is that, like with all security technologies, it changes the attack surface. So the idea is you have some problem that you're trying to solve with security technology, and it changes the attack surface. And the idea is to make it harder for the attacker. So there are always ways around different systems of breaking them. But the thing is it makes it hard. All of these technologies make it harder for the attacker if you use them in an appropriate way.
Yeah,
very important, the appropriate way.
Yeah, I can completely relate to that. I'm more of a security person. I don't call myself a privacy or crypto person, but yes.
Yeah. With all technology, you can have a firewall, but if you put the firewall in the wrong place, it's useless. But if you put the firewall in the right place, it prevents the attacker doing certain things, but you've still got other ways around the firewall. So it doesn't give you perfect security.
Yeah, a good example there would be not configuring it at all.
Yeah, exactly.
Sorry, I'm going out of way here, actually.
But a very true lesson for everyone listening.
Yeah. But Philippa, I think these are quite important points that we are covering. We wanted to go through a couple of use cases and other point I think we wanted to go through also on how to choose which privacy technology to, or let's not call privacy as you were saying, more of PET technologies to use. Yeah.
Okay, it's actually really complicated. So we can kind of well, let's take electronic voting because everyone understands electronic voting. That's a really, really simple thing. You can think of electronic voting as you can use all of these three technologies in electronic voting. So one way you can do electronic voting, which has been used there's this system called Helios, which is used quite a lot in different organizations around the world to do voting, is that what you actually do with Helios is you encrypt your vote. So your encrypted vote goes to the server. And suppose I'm encrypting between, I don't know, candidate A, B, and C. Now I have to prove that my vote is valid. How do I prove my vote is valid? That's zero knowledge proof. So I actually use a zero knowledge proof to prove that I actually valid for a valid candidate. And now my encryption goes to the server, so I can see my encryption on the website. So my encryption, my vote is there, and I can see it's there. Now we want to add up the votes. Well, what we do is we use homomorphic encryption. If we encrypt it with a homomorphic encryption scheme, we can add up the votes, and at the bottom we can say, here is this ciphertext which contains the answer to the election. But we don't know what the answer to the election is. But we know, because everyone can see the ciphertext, this is the ciphertext which has the result of the election. So now what we need to do is decrypt that final vote. Now, to decrypt the final vote, what we do is we do an MPC calculation to do the decryption such that no one person can get access to the decryption key. Because if you gave someone the decryption key, they could decrypt all the individual votes. We only want the decryption of the final sum to be decrypted. So if we do this by distributing the key amongst maybe the three candidates can now execute a multi-party computation to decrypt only that single ciphertext and then get the result of the election. And then everybody's guaranteed that that's the result of the election. So there in that example, we've actually used zero knowledge, homomorphic encryption, and multi-party computation all together. And what we've done is we've used the technologies in very specific points in the protocol to give us the result we want. And so this is the kind of, it's like this amazing security engineering landscape, is that you have a problem you want to solve, and then you kind of use these different technologies in different spaces to actually get the actual final result you want. And these systems for electronic voting have been around for like 10-15 years. So this is quite well established as a combined technique of performing an electronic voting over the internet. You can think of a similar one with auctions, which is a very old thing, which was the first commercially deployed MPC solution was in the mid-2000s, and it was doing an auction, which is basically, you know, one party's got one set of stuff to sell, and another party's got another set of stuff to sell, and they want to work out what the price is. But if they just do an auction, you actually reveal something about your demand and your supply curves. So what you want to do the auction without revealing this information. And that was done in the mid-2000s, but auctions is essentially a mechanism of resource allocation between parties. So we can think of resource allocation as auction, which can be used in all sorts of different scenarios. We can imagine it in accessing stocks, buying and selling various commodities. We can even imagine it as allocating supply chain space in supply chains, you know, how much stuff goes on one truck and whether the truck goes on the boat and so on.
Thanks, Nigel. But just wanted to touch about as soon as we talk about MPC and things like that, and we are also talking about key management and stuff like that also comes in. Yeah, just wanted to touch a little bit on that side.
Okay, it's a very popular topic in MPC at the moment because it's really big. So I was a co-founder of a company called Unbound Security, which earlier this year was bought by Coinbase, which was doing exactly a key management thing. And key management in MPC is really interesting because, so what is key management? Key management is how do you manage and control keys? Now, the traditional mechanism in an enterprise to do this is you store the key in the hardware security module. You store it in a very, very secure place. And what that says is that no one can steal the key. It stops the key being stolen. But actually, key being stolen is not the real problem. Okay. It's key misuse is the problem. So imagine that you're using this key to as the thing that unlocks billions of dollars of resource in a blockchain application. Or imagine the key is actually the thing that's used to do software code signing. If you produce one invalid signature by mistake, your company is toast. Either you've lost billions of dollars that were controlled by that key, or you've put out, you've signed a piece of code that's buggy, and you've destroyed all of the appliances that you've pushed the code out to.
Okay.
So what's really important is not the theft, but it's actually, can we actually embed in a way that the control structure of when we produce the signature goes through certain processes. So for example, if this was software code signing, you might have the developer has to sign it off, his manager has to sign it off, someone else from quality control has to sign it off. It has to be signed off by an automatic bug checking system. And the way this would normally happen is, a bit naively, you would go along and you check off on a piece of paper, check, 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 check. And at the very end, you'd now go, tell the HSM to do the signature. And if one of those checks, which is essentially authorized manually, is invalid or doesn't happen, then you could be making a mistake. Whereas with MPC, what we can do is actually roll it all together, and we can actually say, you cannot actually do the signature unless everybody has agreed and everybody participates in the protocol to say this signature should be produced to authorize the transaction or to sign the piece of code. So we can actually stop a lot of the problems that come from inappropriate use of keys as opposed to key theft. So it's not just about key management in the sense of stopping the theft, but it's actually key management in the sense of key usage. And that's where MPC wins, is because we can guarantee the control chain that you would have normally for authorizing transactions can be cryptographically guaranteed with MPC, whereas with other technologies it can't be.
Thanks. That does help a lot. I'm pretty sure to our audience as well, it should be very helpful. I wanted to move to a slightly different direction. Philippa, I hope that's fine. I wanted to check more towards guidance to a company. So we talked about a case where which technologies to use, but then at the same time, technology is one side, but maybe there's a strategy side also for a company to consider. And do you have any advice on that? I think
so. A number of companies and organizations contact us, and they really need to get advice, because it kind of, you hear me talk and you go, yeah, it's wonderful, we can solve all our problems, of course, but this is not true. And also sometimes it turns out that by inherently in the business processes that are being conducted, or just the workflow that people are currently doing, you cannot translate something into something that's privacy preserving or is good. So a really good example here would be, you see lots of organizations want to process large amounts of data. And they have their team of machine learners, data scientists, they're now called, what the popular phrase is. And so the data scientists go, we want to process this data and do all our, heavy duty machine learning. And then they go, oh, but we're working on private data, so we better secure it. So let's now think about using homomorphic encryption or MPC or whatever. And then you start talking to them, and it doesn't make sense. It's simply because a data scientist, the first thing they do is they look at the data. They see the data and they go, okay, this one's an outlier. this is a problem. Let's do a cluster analysis here. Let's kind of see, they do explore the data. And then they kind of make decisions about what they're going to do, whether they're going to run a cluster in algorithm, whether they're going to run neural network, whether they're going to do this, whether they're going to do that. So there's a lot of human intervention and processing. But if you encrypt the data or you do MPC, they can't see the data. So all that stuff that they manually do is impossible. So their entire workflow has to be thrown out the window. So in some sense, if you could do secure data processing of the data scientist, you could get rid of the data scientist, because the data scientist is the manual person who looks at the data and massages it, and they actually are interacting with the data by seeing it. You give them, if you take away the ability to see it, you take away the data scientist, and usually at that point data scientists go, no, we don't want to adopt this technology, because officially it's because it doesn't fit their workflow. Unofficially, it would put them out of a job.
You're hitting on a very key point over there, actually.
So usually these technologies work when the processing of the data is totally automatic, when you know beforehand what you're going to do. It doesn't actually depend on the shape or form of the data. A classic example here is Boston Wage Survey. There was a survey done, I think, every year in Boston of companies of working out whether women or men are, how much women are paid less than men, not whether women or men are paid different amounts. They are paid different amounts. The question is how much. And so what they do is they survey 200 companies in Boston. And so these companies put their data into a pool, and they produce the statistical results across the whole of Boston. And this is done in a way that is completely automatic. What you do is you just match the jobs up, you take the averages of the salary of the men and the women, there's nothing, so it's completely automatic. And so for that kind of problem, we can apply these kind of technologies, because there's no human intervention that has to look at the data to see what should we do, what you're going to do.
What do you think about the future of these kind of technologies then? Do you think there'll always be this issue of you have to use it for kind of automated processes?
I think it's going to take off. I mean, we see, even on a monthly basis, we see more startups, more applications being used, different things. And it's really, so it comes from, currently the technology has to fit a kind of sweet spot in terms of what you're trying to do and the business process. And so, and that sweet spot's getting bigger and bigger and bigger. But as the technology becomes more widespread, it will be game changing, because these new sweet spots, new business processes come about because people realize the technology enables you to form partnerships.
Yeah.
And if you suddenly start thinking, actually, company A can form a partnership with company B and unlock greater value, which gives them a competitive advantage, you're going to see more and more of these applications coming out. So I think we're really at the beginning of a huge upward tick in the applications, and there are applications that we haven't even thought of, because it's not going to be about securing the privacy. Going back to this privacy, it's not really going to be about securing privacy of databases, which is, like we said, it puts the data scientist out of business. It's actually going to be new problems, new products, new services, new ways of working this is going to enable.
Okay, and that's kind of quite a nice point to end on as we're coming to the end of our time. But very quickly, at the beginning of April, you're part of a Privacy Enhancing Technologies European Summit. Would you like to just end by talking a little bit about that?
Yeah, sure. There's a thing in the beginning of April in Zurich, and I think there's not a repeat, but a similar event happening in the US a couple of months afterwards. And this is going to be bringing together a number of organizations within this space in Zurich to explain. There's going to be roundtables, there's going to be discussions by experts, panels, and all sorts, which enables people to get a much better handle on the technology. So yeah, check it out. There's also lots of other resources online with videos and stuff just around this whole space. Yeah, so there's a lot. If anyone's out there interested, there's plenty of places you can get into this technology.
Great. Thank you so much for joining us today, Nigel. It's been really interesting, and Anand as well. Thank you.
Thank you.